Maybe we should get started with the last talk of the evening or afternoon. So the last speaker is Luis Chacon from Los Alamos National Laboratory, who will talk to us about a 2D-2P multiscale semi-Lagrangian algorithm for fast electron transport with the relativistic Vlasov-Fokker-Planck equation.
Thank you. Thank you very much for the opportunity and the organizers for the invitation. I really apologize I cannot be in person there. I would very much have liked to, but Los Alamos is not quite approving foreign travel yet, so I'm sort of stuck here at home. Anyway, this work is motivated by the simulation of runaway electrons in tokamaks, and I'll introduce that problem in a second. And this work is in collaboration with Don Daniel and Will Taitano. So this is the agenda of the presentation. I'll motivate the talk. I'll introduce the relativistic Vlasov-Fokker-Planck equation, which is just very similar, in fact, to its classical cousin, with a few differences that are noteworthy. And then I'll discuss how we deal with the collision operator, the relativistic Fokker-Planck collision operator non-linearly, and introduce some of the details. It'll be a brief introduction on that. And then discuss how we deal with the relativistic Vlasov equation in an asymptotic preserving way to deal with the really fast electrons that are generated in tokamaks during a disruption. Then I'll verify the solver and apply it to, in fact, runaway electron simulations in axisymmetric tokamaks, and I'll summarize and conclude. So the ultimate goal of this research is to, I'm going to move this around, to mitigate damage from plasma disruptions in tokamak fusion plasmas. The tokamaks, as most of us know, are magnetic bottles that confine fusion-grade plasmas. They are the leading concept for realizing fusion on Earth, but they can become unstable and lead to disruptions. And in the process of disruptions, a large runaway electron current can generate because of the inductive electric field that ensues. These are highly relativistic and very energetic electrons that develop in the presence of complex evolving three-dimensional magnetic fields. And therefore, in order to develop avoidance and mitigation strategies for runaway electrons to prevent plasma-facing material damage, we will require phase-space engineering strategies, which will require in turn robust and accurate kinetic solvers for the electron distribution function. So that's the goal of the project. The relativistic Fokker-Planck equation is, as I mentioned earlier, very similar to its classical counterpart. Here I'm showing the Vlasov operator on the left and the collisional sources on the right. And the collisional sources have this usual diffusion advection form in momentum space, and this is the potential form that we're going to be using. These coefficients in turn come from essentially elliptic solves of the Brahms-Kearney potentials. These are 5 potentials instead of the 2 classical Rosenbluth potentials that we find in the classical Fokker-Planck equation. And these require, as I mentioned, the solution or inversion of elliptic operators in momentum space that are listed here. And then that's sort of the relationship between the distribution function and the H and G potentials that I mentioned. As I mentioned earlier, there are 5 of them. So this is a very challenging system to solve. As is the case in the classical Fokker-Planck equation, we have disparate time and velocity scales. The collision operator is very complex, as they showed, with strong linearities and, of course, collisional invariance with conservation of mass, momentum, and energy, and the strict preservation of positivity. The Vlasov operator, in turn, also requires preservation of positivity, and in this case, it can be very stiff because we have a fast streaming population of. Okay. Can you guys still hear me?
Yes, can you still hear us?
Yes, there was some sort of interruption. Okay, so it can be very stiff, but not always, and really depends on what the collisional timescales are, and that's part of the problem here that I'll be attacking in a second. And of course, it's very anisotropic in that orbits can be viewed as one-dimensional manifolds in six-dimensional phase space. In the plot, I'm showing an actual simulation in 0D-2V or 2P of a runaway electron vortex where you have the bulk at around 0 of electrons, and then you have this really long tail that forms this vortex in phase space owing to the interaction between collisional forces and or collisional sources and also synchrotron radiation forces that actually pull electron back in phase space. And this is actual, of actual interest in physics of runaway electrons. So let me continue with the challenges. Our equation is then of the form shown here with a parameter epsilon that can be much smaller than 1. And therefore is in the so-called stiff hyperbolic transport regime and admits fast oscillatory temporal solutions. And that in turn will require conditioning, and this is well known in the literature. And we seek an asymptotic preserving uniformly convergent scheme suitable for in-principle arbitrary geometries. And here I show the standard diagram of asymptotic preserving methods where commutation and taking the limit of the small parameter commute or should commute. There are a few existing studies on AP, asymptotic preserving methods for stiff hyperbolic systems, and at least here are the two that I am aware of. They're both based on macro decomposition on simple geometries and no collisions. The approach in one is semi-implicit, requires dimension augmentation, which is already problematic for already a high-dimensional problem, and asymptotic condition of the initial condition. And that is in fact a common problem, except here they do it explicitly. Our method will do it automatically. The approach in 2 is Eulerian, is fully implicit and requires iteration. Requires variable augmentation, and the limit equation is a stiff, highly anisotropic diffusion equation, which is difficult to solve. Our approach is in the spirit of reference 2 here, but avoids augmentation, is uniformly well-conditioned and convergent, and avoids iteration. So hopefully I convince you that it's a practical way to move forward. So we'll try to tackle these challenges. We'll start with the drift kinetic equation. It's not really the simplest, it's relativistic. It features some complexity, but it's not the full Vlasov equation. We removed basically the fast gyro motion here. We will write it in integral form along orbits using the Green's function, and then we'll discretize it using a semi-Lagrangian semi-implicit approach. The semi-Lagrangian character comes from the Eulerian treatment of collisions, the Fokker-Planck, relativistic Fokker-Planck equation, plus optionally the electric field and other sources on the Eulerian mesh. And then the Vlasov piece will be dealt with a Lagrangian approach, which is really a Green's function method. It's not the standard Lagrangian approach that we're used to in some of these Vlasov applications, as you'll see in a second. And the semi-implicit character comes from the fact that the collisions will be dealt with implicitly, whereas the Vlasov is basically explicit, although a strange version of explicit. But it does not require iteration, it's just a direct solve. And then we'll demonstrate asymptotic well-posedness numerically and by analysis. So let me begin with the Fokker-Planck collision operator in the relativistic regime. And this is a brief overview, and the paper there has all the details. So we discretize it fully implicitly using VDF formulas, and we do it nonlinearly, and we try to converge it within a time step. We use Anderson accelerated Picard as our solver because it's beneficial for some of the limiters that we need to employ for positivity preservation. And we use second-order conservative finite differences. We do enforce exact discrete conservation properties of mass, momentum, and energy using a nonlinear Lagrange multiplier approach, which we proposed in the classical form of the Fokker-Planck equation in reference 1 here, and we've extended to the relativistic case in the paper that I mentioned earlier. We enforce positivity because it's critical to capture small amplitude runaway tails, and also it's a property of the equation. And we do this in 2 ways. For the anisotropic diffusion component, we in fact employ a trick that was proposed in reference 2 here by Dutoit and collaborators for the classical Fokker-Planck, where you transform closed fluxes in the diffusion, in the tensor diffusion operator, you recast them as advection operators, and then you use an advection limiter on it. And that turns out to work really well to prevent some of the ill-posedness coming from strong anisotropic diffusion. And for advection, we use SMART here, which is well suited for some of the implicit solvers that we're going to be using. All these results in a strongly nonlinear finite difference discretization that we converge iteratively, as I mentioned earlier. The importance of conservation is exemplified here. This is in fact done with the classical operator, with Will Titan and collaborators, and we just showed for a simple relaxation problem using otherwise exactly the same mesh and formal order of accuracy, what happens when you turn on and off the conservation of energy, right? And on the left is the right solution, which compares well against the semi-analytical solution from Braginski. This is an ion electron temperature relaxation problem. And on the right is what happens when you turn off conservation, and basically the solution moves off the manifold and becomes completely nonsensical. So this is the basic motivation for all the work we're doing underneath for the conservation properties. As I mentioned earlier, instead of two classical Rosenbluth potentials, you get the Brahms-Carney potentials, which are 5. They have several difficulties also shared with the classical counterparts, but here, because the domains need to be so long, that they're amplified. The difficulty number 1 is that in our implementation, we nonlinearly eliminate this, the solution of the potentials. This is done because it has particular benefits when you do multi-species that I'm not going to get into. But basically, that requires the solution of these linear elliptic equations at every nonlinear iteration in the momentum mesh. So what we do to address that is to use a very efficient multi-grid solver that converges very quickly. And the difficulty number 2 is that these potentials need to be solved in principle in infinite momentum space. But of course, we can't afford an infinite momentum space, so we need to make it finite, and for that you need far field boundary conditions, which are found from the Green's function solution to the elliptic equations. However, the Green's functions themselves have singular kernels, as we know from the classical case too. And the solution here is in fact similar, is to essentially do a partial analytical integration to find complete elliptic integrals, and then there moves a singularity. So that makes a tremendous impact in the efficiency of the computation of these far field boundary conditions to solve for the potentials. The second thing is that if you don't do anything, by a surface to volume ratio argument, you find that you break the linear scaling that you're seeking, because the cost of these far field boundary conditions scale like the number of mesh points to the 1/2 if you implement them naively. And what we did here is to actually implement them adaptively by having a Gauss-Self-fitting algorithm that finds the optimal number of points to evaluate these integrals at and the location. And then as a consequence, we're able to break this 1/2 scaling, and we end up with 1.1 log n, n to the 1.1 log n scaling. So the details of the potential computation, the far field boundary condition computation are here. We basically start with a few points that we evaluate with our exact formulas, and then we start subdividing those as is shown in this graph here. And then we test against the actual solution, that the integral solution that we know, and by interpolation we compare those two. And then if the difference is large, we keep refining. If the difference is small, we accept those points and we move on. And by doing so, we end up with many fewer points that would otherwise be required for a domain like I'm showing on the right, where you show essentially 43 non-uniform spline knots in the p-parallel axis and 27 in the p-perp axis. And the mesh here in principle is a uniform mesh. In this case is 64 vertically and 2048 horizontally, so many fewer. And the scaling of the wall clock is shown here, where we indeed verify that per nonlinear iteration, the cost is of n to the 0.1 log n. So quite reasonable. And this is for two problems. On the left, let's see, on the right is the actual number of spline knots, where you see, that the scaling is very, very mild with a number of degrees of freedom. So this breaks that curse of dimensionality for the computation of these far field boundary conditions. Here I show some actual results for the collision operator, and I'd like to highlight two. The first one is the number of iterations per time step. As we increase the number of processors, that's NP right here, and then I'm commensurately increasing the mesh, as I'm showing here, so it's weak scaling. And you see that the number of magnetic iterations really scales very weakly with the problem size, essentially. And also, the wall clock time scales accordingly very weakly with the problem size. So it's basically not quite constant. It picks a bit of scaling, but very, very, very mild. So for verification, we've tested this against several relaxation problems, and we've checked our conservation properties are in fact preserved, as shown here on the right, to nonlinear tolerance, which is all that you can expect from these kinds of methods. We've also tested that the approach is spatially or in momentum space, really second order and also temporally second order. And this is the same example as I showed earlier, where we actually applied this to a problem that's been looked at before by collaborators at Los Alamos, and we found really good agreement with their solution. So we're fairly confident that we're doing the right thing on the collisional operator. And now I'm going to transition into the relativistic Vlasov component of the problem. So as I mentioned earlier, we consider a drift kinetic evolution equation, which is exemplified or stated here. And this has as invariants the magnetic moment mu and the energy E. And we consider the simplest guiding center orbit equations, where we really essentially neglect all the drifts and we just keep the magnetic parallel velocity. And then we have for the momentum update P parallel, we have the electric field and the mirror force. And these two equations of motion conserve magnetic moment and energy, as I'm showing here, and they also satisfy incompressibility in phase space, which is important. So with these simplifications, our distribution function can actually be considered a function of the flux, the poloidal flux psi, the angle around the poloidal surface theta, and then two momenta components, P parallel and P perp. And at this point, the flux actually can be considered a parameter. So it's really 3.5 d, if you wish. But we will be sampling various psi's in our problem so that we end up getting a two-dimensional 2D-2P solution. So as I mentioned before, runaway electrons are fast, and they travel at near the speed of light. And the standard solution in the community for this has been to go to actually the limit asymptotic equation, which is so-called the bounced average equation, which is really valid strictly for nested integrable flux surfaces and hot enough plasmas, such that there is enough scale separation between the transit time and the collision time of these electrons. In other words, electrons need to bounce many times for a given collisional characteristic time. But it does not work when you have complex three-dimensional magnetic fields or when you have insufficient timescale separation, for instance, due to cooler plasmas. And this was demonstrated numerically in reference 1 below. So we seek a runaway electron solver that can work for arbitrary plasma temperatures and in principle three-dimensional magnetic fields. I say in principle because we have not extended it to 3D spatial dimensions, but as you will see in a second, the formulation itself lends itself to this kind of configurations quite straightforwardly. So the formulation must be well posed asymptotically, as we all know, because we're going to have to deal with these plasmas where the temperature varies in time, and it can.
We just lost your audio. Oh, yeah.